Yeah.
All right, so welcome to Excellent Adventure. This is going to be the first lecture. I don't know if I should be talking to the camera or you people. I'll just talk to you people during the interview.
That's us, yeah.
We're going to have weekly, hopefully, Excellent Adventures. So we're going to have lectures from the upperclassmen teaching the underclassmen things that they are, they feel particularly confident about. Maybe things that you haven't seen in your classes, things that we've picked up along the way in our education. So this is supposed to be, primarily cool talks, just interesting things, and cover over a lot of information that hopefully you won't understand all of it. Hopefully I'm giving you a place to jump off from for your own research and learn things on your own. So hopefully you find some of these things interesting and you'll pursue them on your own. So since we're on YouTube again, if I say anything wrong, please tell me that I'm wrong so that way this is not online and we have to fix this or something. All right, so this is on intuitive quantum mechanics. So a lot of people say that quantum mechanics is not intuitive by any means. It's the most crazy thing. It doesn't make any sense. Schrodinger's cat and all that wonderful stuff. But it actually makes a lot of sense if you see things from the historical perspective. When the physicists were inventing quantum mechanics in the 1900s to 1925, that area, they were using current theories that we had from classical mechanics and just extending them just a tiny bit, just pushing them past what we knew at the time, and they found all of quantum mechanics fell out. So hopefully you'll be able to see that train of logic as well through what I'm going to talk about. First, I'm going to cover representations because I think that's very important for understanding what quantum mechanics means. Is that if any of you were in Dr. Uzer's atomic physics class, you probably heard this last week, just the general idea is that we have things in math like a vector. And this vector is this abstract physical or mathematical concept. It's just this thing that exists in math, and we can do things with it mathematically. And we can assign to it, let's say we have a Cartesian plane here, and the vector extends up here. Some amount A, some amount B in the j hat direction. And we can say the vector V is equal to A I hat plus B j hat. But this is not entirely true. This is just one representation of this vector. This is the representation of this vector projected into Cartesian space, into configuration space. But there's many different ways to look at this vector. And depending on how you look at it, you can see different parts of its personality and what it actually means. So this same concept stands for whenever you see the wave function in quantum mechanics. This is just some thing, some mathematical thing. And you can do things to it, and you can project it into a certain space to learn more things about it. But you don't necessarily get the full information by just looking at it or just thinking hard about what you think it may be. It's like looking at one side of a building. You look at the building of Howie, we've got on the inside SPS and wonderful people doing wonderful things with knowledge and things. But taking a representation, playing Smash Brothers, taking a representation of psi, let's say in the configuration space, is like looking at the outside of Howie. Maybe you're just looking at the building itself. You learn a lot from that, and you can do some stuff with that, but that doesn't teach you the full information about what psi, the ket, is. All right. So, Newton's second law, all of you know, is F equals the change in momentum over time, dp/dt. And the first law from Wikipedia is, when viewed in an inertial reference frame, an object either remains at rest or continues to move at a constant velocity unless acted upon by an external force. So some people would say that this is just a special case of the second law whenever you set the force equal to 0. Then you just have a first order differential equation. This means that momentum p is constant over time. That's the first law. It's not just that. I see it as it's setting up an inertial frame in which Newton's laws may work. So the first law sets up the universe, basically, the mathematical infrastructure upon which we may apply the second law. So just in this way, quantum mechanics exists in something known as the Hilbert space. So this is just like Newton's first law with inertial reference frames. It's just like special relativity with Minkowski spaces, with Minkowski metric. And within this Hilbert space, we have Schrodinger's equation, which tells us how particles move. You've probably seen this. It's that beautiful, crazy-ass equation. All right, so I learned this next part from Dr. Ian Gatlin. For those of you who were in my Quantum 2 class, it was awesome, because he taught us this derivation that he learned from his professor, who learned it from his colleagues, his or her colleagues at the time. So this is probably straight from, a good source of where this idea and the intuition came from. So in 1905, Einstein stated that light propagates as a wave, but it also interacts as a particle. In 1924, de Broglie, whatever the French guy's name is, found that electrons propagate as a particle, but they interact as wave. That means we have this interchanging of wave-particle duality, and people always talk about that sort of thing in quantum mechanics. So let's just say we have something, some function, a equals e to the I kx minus omega t, a wave in one dimension where k is the wave number, lambda is the wavelength, and omega is the angular frequency. All right, so this is just some matter wave, it's just some general thing. So from Einstein, we get the idea that energy is equal to h bar omega. So that means that omega in this equation is equal to E over h bar. All right, cool, woo. And from de Broglie, we have the de Broglie wavelength sort of thing. So we have that lambda equals h over p, which is equal to 2 pi h bar over p, just changing it out to Planck's reduced constant, which would mean that our wave number is equal to, because that's 2 pi over lambda, would be equal to p over h bar. All right, wonderful. So we have these two variables. We can actually rename our matter wave as being a e to the I over h bar px minus et. All right, so yeah, and this is in no way supposed to be rigorous at all. So if you have any quarrels with this, just yell at me later. I don't care. So we have this expression for what a matter wave really is. If we were to take the first partials of this matter wave, trust me, this goes somewhere. It's actually really crazy interesting and makes no sense and makes you scream. Partial f on x, you end up getting I p over h bar times our original function, because that's how derivatives work. Yes, good. All right, and then if you take that partial on time, it's been a very long time since calculus, is minus I e over h bar times our function. So let's take the second partial on this. That would just be I p over h bar squared f, which is negative p squared over h bar f. All right, cool.
H bar squared.
Yeah, good, thank you. Cool. So we have our original equations that we had from before. No, we have these equations. Wonderful. We have, yes, sorry, energy is equal to kinetic energy plus the potential energy. And the kinetic energy is known as p squared over 2m plus the potential energy. All right, and we can take this formula that has this partial of f on x squared in it and solve for p squared, and then we can also plug in this whole expression into this expression. And we basically combine all of these equations into one lovely, beautiful, awesome equation, and we end up getting that. You can check this yourself if you don't believe me, but deal with it. This beautiful monster here. So you may not recognize this if you haven't taken quantum mechanics, but if you have, holy hell, that's the Schrodinger equation. It actually falls out from just taking the two assumptions from Einstein's relation and de Broglie wavelength. And you have the Schrodinger equation that falls out. So we introduced the matter wave without actually explaining what it is. What does it mean? What the hell does it mean to even have a matter wave? We had this f equals a e to the I h bar over, all this stuff. But yeah, what does that mean experimentally? So if we were to shine particles at a wall, let's say we just shine them here, there's a lot of particles here, and then there's fewer and fewer and fewer and fewer, something like that. You have some intensity that goes over all of this stuff. So the number of particles that you can expect to find is equal to if you integrated this intensity that you find over the area that you have, where the eta will be your infinitesimal area L1. That's the number of particles. If you just had one single particle, what we posit is that this equation will still hold for a single particle. Each particle itself has a wave associated with it. Then this could be one particle. So one particle equals the measure of the intensity over this region. But that's only for the infinite interval because the one particle is spread over all of space. So if you were to integrate over from one section to another section, you just have a percentage of a particle. And the intensity from waves, Gilly knows this sort of thing, but I definitely don't know waves that well, but the intensity is proportional to the mod square of the amplitude of the wave. So from this, we actually see that the percentage of a particle is equal to the integral of the mod square of the amplitude of the wave. Max Born's wonderful interpretation of this sort of thing that I think he won a Nobel for was that this percentage of a particle corresponds to the probability of finding the particle in that location. So what we see is that the probability of finding a particle at some location on here is equal to the integral of the mod square of its amplitude times the infinitesimal area element. If you haven't taken quantum, that doesn't make too much sense, but if you have, hopefully you're blown away by the fact that you can actually interpret A as being psi, because the integral of psi squared is the probability, because psi is the probability amplitude. So that's awesome. Now we have a better interpretation for what the wave function actually is in quantum mechanics. But what about the Schrodinger equation? What the hell does that mean? What does it mean now that we have this wonderful, beautiful, crazy equation with I and an H bar and all these fancy things? That comes a little bit more naturally if you think of, consider the diffusion of the density dynamics of a material diffusing in some medium. So the equation for diffusion is equal to this lovely creature here, where d is some diffusion constant and phi is the concentration of something. So if we set d equal to I h bar over 2m, just randomly set this diffusion constant into this lovely piece of work, we end up with the equation I h bar d phi t equals p squared over 2, h bar squared over 2m, now the squared phi, which is the Schrodinger equation for a free particle, not in any potential at all. So what the hell does that mean? That actually has very questionable interpretation, but what you could maybe think of this as is that a free particle under no potential acts as if it's a diffusing concentration of some material through space. But the rate at which it's diffusing through this constant of spreading out over space is complex. That's insane, but that's what quantum mechanics is. So you can actually think of a particle itself as just expanding and diffusing through space, or complex space. All right, so that's just interpretations. I thought those were pretty important to cover. I didn't have those in until last night, actually. This is where the history part comes in. So at the time of inventing quantum mechanics, we started with Hamilton's equations. If you haven't heard of those, they're extremely wonderful, and they're good, and they're simple, and it's basically negates everything you've ever learned. Doesn't negate, but makes useless everything you learned in Newtonian mechanics because they're so much better, and you don't have to worry about forces. So for position q and a momentum p, you have these equations where h is something known as the Hamiltonian. It's not in general the energy, but you can interpret it as the energy of a system. And mathematically, h maps something known as the cotangent bundle onto the real line. For math people who want to learn that sort of fun, happy thing. All right, so deal with it. No, I'm going to name drop a lot of fun, extra happy things just in case you want to look into them later. So cotangent bundle comes from symplectic geometry, which is an amazing branch of, I guess that would be mathematics. And it's insane. It makes all of classical mechanics seem trivial once you actually study the math behind it. Because it's like, oh, well, obviously the universe has to work in this way. So it's really cool. It's interesting. So you should really look into symplectic geometry. So if we have a function of this position and this momentum, if we have two functions, we define something called the Poisson bracket as being this crazy formula. It doesn't look like it makes any sense, and there's no reason for it to have this form, you would think. All right, so there's a reason for this later, and if this notation looks familiar to you, it should, because it's unsettling. So this is the Poisson brackets, this crazy notation for something. So let's take the full time derivative of a function f, which is it's a function of the argument's position and momentum. So the full time derivative is equal to the partial differential expansion of it. Okay, this is just taking the chain rule, basically, and expanding it out. And we can substitute Hamilton's equations into this formula. And you see that this lovely beast that comes out after substituting Q and P directly into here looks exactly like the Poisson bracket. So you end up getting the Poisson bracket between your function f and the Hamiltonian. So again, for those of you who haven't taken quantum mechanics, this is just, yeah, whatever. Sure, I guess you just did some math. But for those of you who have, you'll notice that this looks a damn lot amount like the Heisenberg equation. The Heisenberg equation, I derived that stuff later on in the packet. I'm not going to do that here. Is this. This is the time evolution of some operator in a quantum system. This is the time evolution of some function in a classical mechanics system. So we've got this, this change of notation here. This is the Poisson bracket, and this is the commutator bracket. And then we also have an IH bar in here, and God knows where that thing comes from. But that's the transition into quantum mechanics. It's basically the same system going on here. It's just you have this constant that basically chooses which, it's called a Lie algebra that you're in. And then you have an I, which just pokes his nose right into your system because deal with it. Yeah, correspondence. So, with these equations, we can change our Hamiltonian to anything we damn well please, as long as we can maintain the same equations of motion. Because the Hamiltonian is not something that we observe in physical space. We observe the equations of motion, or at least that's what we care about. So you can change that Hamiltonian, you can change your coordinate system, you can change anything. As long as you have the same equations of motion and the same physical system that emerges, you're totally cool. And this makes total sense within your mathematical framework. So there exists a wonderful set of coordinates called action angle variables. You should really look into these because they are beautiful. So J is known as the action, and we have phi, which is the angle. So for like a harmonic oscillator, for instance, if we were to plot this in phase space, it would oscillate around like this. Well, within these variables, you have an angle that moves around, and you're basically just looking at your system from a different set of coordinates. It's just a fancy coordinate change that doesn't really change anything.
What's the action?
The action is just the name of this variable.
Is it the magnitude of that vector?
Nick, what is the action in this case? I should definitely know this. I just took class.
Yeah, I mean, the name action doesn't really correspond to anything. It's just a variable. It's a variable that controls the dynamics.
All right. It is like, there you go. Cryptic answer is,
I think it doesn't matter.
it corresponds to a variable.
I mean, it has to be the magnitude, right?
I'm not sure what it is. I don't want to say this magnitude because I'm on camera right now, and if I lie,
You move to a
That's the internet.
Hamiltonian system that depends on one variable, and that's J.
yeah. Basically, you've changed your Hamiltonian such that Hamiltonian is only a function of this single variable.
So it's a parameterization, and that's why.
Yeah, you get the inverse. You're just changing variables to a different system. It doesn't matter really how you make this change of variables. It's called a canonical transformation. It's something that just preserves your equations of motion. So the reason I'm bringing this up is when quantum mechanics was first done, there was this ritual for solving all these problems. You've probably seen the Bohr atom derivation of how he derived the orbits within hydrogen, and they also did some ghetto explanations of how the harmonic oscillator would work. But there's no real ingrained explanation of how to do this every single time. There's no quantum mechanics infrastructure underneath all of this. It was pretty much be a good physicist and then do math. And that's how you would solve quantum mechanics problems. So they didn't really understand what coordinate frame is quantum mechanics taking place in. You could change this all the time, and it doesn't make any sense. Why would it have a preferred, or it doesn't even have a preferred method? They found it. Quantum mechanics works in action angle variables, or at least in the old quantum theory it does. So when you have some crazy system of momentum and position, you may not necessarily find the quantum mechanical analog immediately, but if you transform it into action and angle variables, it comes up extremely nicely and immediately. So action is defined in this coordinate frame as 1 over 2 pi the closed integral of p dq. So let's use this system on the harmonic oscillator, because every physicist should use the harmonic oscillator all the time, because there is no other problem. And if you think that there is another problem, then you need to take quantum field theory. Where they're just like, I'm not even going to solve the harmonic oscillator. Everything is a harmonic oscillator now. You just deal with it, everything, all the way down.
What if my problem is I need to pay rent? Does this happen every month?
Expand about equal. Yeah, that's periodic. Expand around the day you have to pay rent. So the Hamiltonian for the harmonic oscillator in one dimension is this fancy beast. If you haven't seen that, go see it. You see it here. This is position, this is angular frequency, a mass, momentum, and this is the number 2. Let's set this to be some constant value E, because we don't, it's just chaotic. If you just let something have as much energy as it wants, it's terrible. Don't ever do that. So we're going to set it to be E, set it to be a constant. And now we're going to solve this whole system for, well, first I'm going to write out my J against that way you see it. This is what the action was. We want to solve for P, because we want to do this integral and transform into action angle coordinates. So you solve for P. I'm just going to divide it, because math, this is not math. E minus 1/2 m omega squared x squared. All right, woo, we got P. And then our integral is just going to be the integral of this, 1 over 2 pi. That's our action. Integrate that over x. All right, and I'm not going to solve this integral either, because that's math. And you make some substitutions, whatever, and you end up with J equals E over omega, where omega is equal to d phi dt. And there's variable substitutions, don't worry about it. This is how you do math. I'm sorry. All right, first substitute x is this thing, then you have the time derivative of that, that's omega, and then you end up with this. This is the action. All right, that's wonderful. So how do we make the quantum mechanical analog of this? This is just fully classical at this point. Everything's classical mechanics, it's just a fancy notation. Nothing is fancy about this besides the notation. Quantum mechanics dictates, this is just in h bar. Bam, you're done. That is now quantum mechanics, because if you solve for this, you get E equals in h bar omega, which is the energy of the quantum harmonic oscillator off by 0-point energy, 1/2 m, or 1/2 h bar omega, or if you're in quantum field theory, infinity. So that's awesome. That shows how wonderful and easy it is to get quantum mechanics from classical mechanics. This probably doesn't make too much sense to you. This is from graduate classical mechanics, which you should definitely take before you graduate. It's wonderful, especially from Dr. Kennedy. All right, yeah. So action angle variables, you should look those up and learn how to use them. And use them on your Physics 1 homework.
I'm done with that class though.
What?
We'll see what Professor Joe is.
Just use it in whatever class you're in. The TA, who's probably an engineer, is going to love it.
No, she's physics.
For honor.
So Heisenberg made this wonderful expansion to, in addition to quantum or classical mechanics at the time, to expand it into quantum mechanics. That was a terrible sentence. What he did is he said that instead of just a variable being a variable of some sort, this thing, see, I love it, he's just going to Fourier series it, or whatever, Fourier expand. Because that's what we do with things that we don't understand, is make them more complicated. And he added a more complicated set of rules on top of it. And it was extremely complicated, nobody understood what was going on with all of these variables because he had a very detailed set of rules that ended up replicating exactly quantum mechanics. And he had this list of ways that you can multiply these indices, basically, or these arguments within the functions. And it had to be done in such a way to produce reality. So there's a derivation of a lot of this, but I'm not going to go over it. It's in the notes if you want to see. But if you transform your position and momentum coordinates into a Fourier expansion, into a canonical transformation into action angle coordinates, you will receive some stuff I'm not going to write down because it's a lot more math. Yeah?
So position and momentum are Fourier conjugates of each other, right?
You know that from quantum. Don't think that yet, though.
Well, I know that from quantum, yes. Well, the question is, so are you saying that you can take position and Fourier it to k-space or whatever it is going to be, and then you also take momentum and Fourier transform that to, like, are you saying that those are, can you just repeat what you said?
All I'm saying is just replace each of these letters with, we don't know anything about momentum and position being conjugates yet.
Okay.
And then we also have P is equal to but each of these have the arguments in there, I just didn't want to write them again. If you do this, and then you perform the integral of this integral, you end up with action angle coordinates. And then once you have this, you set this equal to, for more information you can just read the notes, it explains it a little bit better. You set this equal to NH bar, which is the one quantum requirement that we're putting on this, is that you set the action equal to some constant integer value. And you end up getting, this is wonderful. I'll just write this more out. Yeah, it's going to take a while to deal with it. They really didn't have much to do back then, so they just did a lot of math. They didn't have computers or anything, so they spent their spare time doing this. He ended up with this expression here. And he just, he didn't understand what was going on here. This was Heisenberg at the time. And he got this expression here with these arguments being in such a way. And he showed this to Max Born. And Max Born was like, I have no idea what the hell's going on either. So he read it for like 8 days. And he was on vacation, I think. And then suddenly it appeared to him. He was like, whoa, I know exactly what you're doing here. Oh man, this is great. He learned this in a math class many years prior in his undergrad. He realized the requirements that Heisenberg was placing on his multiplication was matrix mechanics. At the time, physicists didn't know matrices. It's insane. I was blown away when I realized this. 1925, physicists had no idea. I mean, astronomers did because they, I don't know, planets or something. But generally, physicists didn't have any idea what linear algebra was because I guess it wasn't useful to us at the time. So Max Born had previously heard that in one of his math classes, and he was like, whoa, you are doing matrix mechanics right now. These are not arguments within a function. These are indices of a matrix. So what you actually have here is a commutator between P and Q, if you expand P and Q to be a matrix. And this is the fundamental commutation relation of quantum mechanics. So in most classes, you'll just be like, this is an axiom, deal with it, go with it. But this comes naturally out of classical mechanics if you just impose these weird, strict rules upon your classical mechanical system. That doesn't make any damn sense. Why would we just expand our idea of what momentum and position are to matrices? So, to understand the universe, you have to look at it from different points of view. Previously, we had looked at momentum and position as just being either numbers, or we would think of them as vectors, or at least before 1925, we didn't know what vectors were. We thought of them as a series of numbers in a line. But to get the full grasp of what reality actually is, you had to expand your concept of what these numbers were, and you had to expand your algebra, basically, to matrix mechanics. And now this will hold within it classical mechanics. That's what we have, and that's what we use to derive to get to this point. And there's some principle called Hankel's principle of permanence. And it says whatever algebraic forms are equivalent when the symbols are general in form, but specific in value, this is actually an awful quote, but specific in value will be equivalent likewise when the symbols are in general value are as well as in form.
Can you say it in English, please?
I thought this was
It's supposed to mean something though. So what it means though is that whenever you expand your mathematical system, which is what was required to understand physical reality, you lose some properties. You lose some things that we really loved to have. Like, we really love commutativity. It's really nice. You would love to just exchange P and Q all the time, all willy-nilly, but you can't, because that's not what the universe says. And you cannot impose upon reality your intuition from your senses. You have to impose upon it your intuition from a different representation, from a different view. You have to look at things from a different set of eyes. And you realize that you have to actually expand your algebra to get to this point. And according to Heisenberg, almost every progress in science has been paid for by sacrifice. For almost every new intellectual achievement, previous positions and conceptions had to be given up. Thus, in a way, the increase in knowledge and hindsight diminishes continually the scientist's claim on understanding nature. So I hope this was understandable. I mean, I'm done. I've got some more notes that are in the back of here. You're welcome to read them. There's more details throughout. But thank you for your time. If you have any questions, I'm willing to answer those. I apologize, this is super theoretical. This is to make up for Casey's experimental talk last time where he taught too many people about jank science, and I had to weigh the balance in the other direction and show that math is really powerful too. What?
I was going to ask about the experiments.
There were no experiments done in the making of quantum mechanics. We took some physicists and stuck them in a dark room, and they came up with this all on their own. It's fantastic, isn't it? No, but really, it's kind of cool because when you look at it now in hindsight, obviously 2020, you can see that there is a mathematical structure upon which all of quantum mechanics operates. So if you do all sorts of fun Lie algebra things, the math guy knows these sorts of things, I'm sure, much better than I do, but I've glimpsed at them and they're awesome. If you do Lie algebra things, you find out that there's some constant that will decide which algebra that you're sort of working in, or at least from my interpretation that I found out. In quantum mechanics, this happens to be h-bar. I don't know where that one came from. I think that's experimentalists. They can figure that one out.
Planck.
Planck's constant.
Just straight from Planck.
Straight from Planck. He thought it up one day. He's a good guy. Yeah, any other questions? Yeah, Arthur.
So, is there a correspondence between the second quantization and classical mechanics?
All right, so second quantization. Look, man. No, I'm not going to talk about second quantization.
Right.
That's upper level quantum mechanics, and that comes from more field theory approaches. So back when I had the harmonic oscillator, so that's not just one. Imagine that everything you've ever seen, even to its smallest scale, is a harmonic oscillator.
Is that a harmonic oscillator?
That is everything as you are. And particles are nothing but excitations in this field. So when an oscillator, oscillates, it's got some energy, and that energy propagates. That's a particle. And when you're dealing with that, that's second quantization. And I don't know if classical mechanics is happy with that.
Hey, let's talk about commutation, because I feel like that's important.
Commutation? Do you guys know what commutation is? I don't remember what.
I know for a fact I didn't when I was at least a sophomore.
I've been here for so long I don't remember what
No one.
It's quantum one.
what people know.
Yeah.
Commutation. So if you have a matrix A and a matrix B, the commutator between A and B, you can't see this at all, but deal with it, is equal to AB minus BA. That's just by definition. That's what it is. So what you have here is that IH bar equals PQ minus QP. So normally in classical mechanics that would just be 0 because you can commute P and Q, and you have PQ minus QP is PQ minus PQ, and that's 0. But reality says no. So the idea is that you have to look at reality from a different setting. Basically, it's not what you see at first glimpse. All we're seeing in classical mechanics is a certain view of reality, and you have to actually stand back and look at the representations that you're looking at, and switch it maybe to a higher algebra, to matrix mechanics, and you'll end up with quantum mechanics. And it's fantastic. Anything else?
Is there a higher form of algebra?
Yeah, you can keep on doing stuff like that. So you weren't here, I don't think, when Dr. Wood gave his talk, but he talked about quaternions, which is so Hamilton came up with these wonderful things, these quaternions, and it describes so much. The same guy that did Hamilton's principle or Hamilton's equations and things. It was so good, quaternions. They worked so well, and he was able to learn so many things that had these great commutation relations that had to do with expanding I, the complex number, to the square is -1. He wanted more things that would do that sort of thing. He was so excited, he got it. He etched it on a bridge and stuff. And 10 years later, Heaviside and Gibbs came up with vector calculus. And that was it. No more quaternions. So we lost quaternions. But quaternions are the first expansion, according to Dr. Wood, if I remember correctly, of our regular rules. And then you can expand quaternions again to octonions, I believe is the second one, and then maybe sextonians, something like that.
Yeah.
But each time you expand your algebra to a higher and higher dimension, you lose another property. So in quaternions, you lose commutativity, I think.
No, you lose commutativity when you go to complex numbers.
Okay, yeah.
Oh wait, no.
No, quaternions lose commutativity.
Yeah.
Quaternions
it's
lose commutativity.
They gain anti-commutativity.
Next one gains, like, it loses associativity, which, something like that, and that's just chaos. And then you can keep expanding your algebra to different things.
Lose multiplication.
What?
Then you lose multiplication.
You lose all is lost.
Just a husk of a human being.
Oh, yeah, so, to explain better why I comes into being, there's something in the extra stuff section that you may want to read on your own, is that when you're doing canonical transformations that I had before, of just changing your coordinates to different systems, you end up with some matrix, it's called the J matrix. And this J matrix is such that when you square it, you get -1. Well, you get the minus identity. So, what else when you square it do you get -1? I. Okay, well that is fantastic, right? Because when you look at this and you're like, oh man, is that the matrix expansion of I? Please, what is this? So you may want to read through that because it's really interesting because that actually comes straight from classical mechanics, that you get this J matrix that pops its head in there. So if you're wondering why quantum mechanics has I's all over the place, first, complex integration, because Cauchy does 2 pi I all the time. And then you have J matrix, which when it's squared is minus the identity. All right, so anything else, guys? Cool. All right, so thank you for your time. Next week is going to be Robert, I believe. No,
it's Nick.
Nick is going to be talking about, I'm guessing this is a 3-part series on quantum mechanics. He's going to be talking about much more theoretical quantum mechanics and particle physics in particular, like Feynman diagrams.
It will be more phenomenological than theoretical.
I dictate what you do.
So, I mean,